Hello, everybody. Uh, Thank you for joining us this evening, morning, wherever you are in this world. Um, just 1 second. So, welcome to the OffNote Labs AI Talk series. We are very happy to have Gaurav Chakraborty talk to us about recommender systems, his experience across building recommender systems across several domains, and And before he starts, some of you might be familiar with OffNote Labs. I'll do a very quick intro to OffNote Labs. I'm Nishant. I'm founder of OffNote Labs, and I'll tell you very quickly about our mission and then hand over to Gaurav. So, hope you guys can see the screen. For those who are not familiar with AirMeet, there's a toolbar on the right hand side. You can use the chat to communicate and ask questions, and there's a raised hand icon also, which you can use to speak on the mic and talk directly. Um, Given that we are going to have good attendance, we recommend you use the chat to put in your questions, and I'll relay them to Gaurav uh, in a batched fashion. So, okay, so quickly about OffNote Labs. Thank you again for those who are joining, and very happy to have all of you here listen to this talk. OffNote Labs is a make it bigger. Uh, it's a platform for doing research without boundaries. This is the end of it. This is the beginning of it. Normally, people have a single slogan. We have two of them. It's a home for independent innovators, researchers, and builders, and senior researchers helping young researchers grow and shine. So, like I said, it's a platform to do research without boundaries and individuals to learn research. There's no kidding and no PhD involved here. It's open to all engineering disciplines and students who are who are ambitious and eager to learn about AI, deep learning, and build real systems. Quick premise behind why we started this platform that I guess most of you are familiar that there's tremendous democratization of knowledge in the field of machine learning and deep learning that has happened over the last 10 years. And with this democratization, we have seen emergence of eager young self-learners who dig into stuff, read papers, build stuff, try out code on their own. And what we there are AI clubs in almost every university now, uh, where students work with their own self-initiative. And our belief is that with mentoring, they will really rise and shine. And that's one of the main goals of labs, to help them get mentored by people who are more experienced in doing research and building cool stuff. And research might seem to be a more academic initiative, but our view is slightly different. It's far more pervasive. When you do research, you learn to build your grit. You learn to deal with uncertain problems and flourish in uncertainty and deal with it. You also learn to discover your own paths, your own taste for problems and tackling them, and work according to your own values of impact, the kinds of difference in the world that you would like to make at a personal level. So by doing research, we hope that we will impart all those traits. So the platform is meant to bridge the young researchers with mentors. The young researchers, like I said, eager to learn and become experts, build cutting edge stuff, and the topmost quality that we need is being self driven and pushing beyond their comfort zones. And mentors, we invite mentors who are willing to share their knowledge, passionate to impart and help young researchers, and plus do research without institutional constraints that they and problems that they are really passionate about, and help young researchers build, uh, grow and learn from them. We part of our building the platform, we have this AI talk series where we invite industry experts, researchers, and builders who are very passionate to share their learnings and experience. And the talks are somewhere between a traditional presentation, which if you've been part of research labs or just conference presentation, and conversations like podcasts. So we keep things really interactive and have the audience really learn from the speaker. And our audience typically is very technically engaged. You can go to our YouTube channel and watch the previous talks. They're on wide set of topics and very interesting. And audience, you'll see that they're very technically engaged. And again, the premise, the background behind the whole thing is that we take delight in unraveling the experience of research and innovation, and celebrate the innovators and researchers and experts. That's one of our primary goals. So with that, yeah, you can check out our website, read our research articles, Medium, OffNote Labs. We are on LinkedIn. Follow us, Twitter, Instagram, and please, if you know of like-minded people who like to learn and do cutting stuff and delve in AI, please help them connect to OffNote Labs. With that, I will give the mic to Gaurav. Again, thank you, Gaurav, for agreeing to give this talk and share your experience. We are very, very happy that you could join us and talk about your work.
Well, thanks for having me. And I wanted to sort of congratulate and encourage you and the community, OffNote community. I think, like I was telling you yesterday, I wish there was something like this when I was in college. I think it is a privilege for both sides, both for mentors to be able to have high leverage, to have impact beyond themselves, and for students to be able to aspire to publications and research that people can use everywhere. So today's talk it will cover all three aspects. It'll cover machine learning research aspects, it'll cover infrastructure, actual implementation aspects, and it'll also cover product design, product management aspects. And I'll come to that the reason for that, but just to sort of give you an overview of the talk first. First, I'll sort of introduce myself, and then we will go into the product aspects. We'll talk about why recommendations are pervasive and have been transformative to the industry. We'll talk about our history and the foundations we're standing on, infrastructure, some grounding of core ideas in recommendation systems. As you can see, we'll go into implementation also. And then we will sort of say how launches happen, actual implementation in companies like Google. And then we will slowly make our way towards graph neural networks. So I wanted to give you guys a preview to tell you sort of, it's not just research themed. I'm trying to bring together like all the areas that actually make impact, that need to come together to make impact in industry today. Okay, so about me, I was mentored early on. I was shown the light that I was doing a theoretical work, and it's great, but I was also shown how that could apply to industry. That's basically my theme today. I want to show not just the theoretical work, but also how it applies to industry, how it can translate to successful careers, how it can translate to successful businesses or even new initiatives. So PhD, I was doing a PhD at UPenn, dropped out, spent 15 years in high frequency trading. Earlier, I was one of the first to use machine learning at Tower Research Capital, it's a high frequency trading firm. and then started my own. Then started a firm which applies this, but also now packages this, and this is QPlum, which packages this as a service to individuals and even pension funds. Then I spent 2 years at Google and Waymo. The part at Google which applies most to this talk was I was leading personalization and in general the machine learning aspects of personalization in Google Assistant. I was also the end-to-end lead for recommendations. More recently, I'm a founding member and ML lead. I'm a team lead at DevRev. We have global offices, and if you are interested, please do reach out. So, as I mentioned, we'll talk about machine learning aspects, infrastructure, actual implementation, product. We will not go into extensive math formulas, partly because that there are resources for it, and it needs a lot of prerequisites that a talk does not do justice to. But I have resources I have linked to, and also you can reach out to me in follow-on conversations. Some of the things that that you should look at if you're interested in this field are very nice tutorials from Google, all the three at the bottom, on actually applying their state-of-the-art methods. Okay. Before I get into these slides, as I mentioned before, if you have questions, please add them in the chat. I'll try to answer them at the time.
Yeah. So if I may just remind the audience, so there is a chat icon on the right hand side. You can free flow your questions right there. I will relay them to Gaurav periodically. And please feel free. And we know that this is a virtual medium and everybody is sort of reserved and all, but please treat it like you were talking to Gaurav. This was a live session, and throw in questions. It gets very interesting that way. Okay, Gaurav.
Yeah. So now let's ground things a little bit. What if this were in a room? I would have asked you guys questions, but due to the medium, I'll try to answer them as well. So, what is a recommendation? A recommendation typically means you have a user has come in and they have not expressed an intent by a search query, and we are trying to guess what their intent is and provide them options. So in search, they explicitly provide an intent. However, even that intent, like for instance, if I search sports podcasts, that intent should be like sports for me might mean different than sports for someone else. So that intent could be interpreted in a personalized manner. And personalized. So first, we talked about recommendation. Recommendation need not be personalized. Top 10 movies in theaters right now is a recommendation. It's just not personalized. Personalized recommendation means top 10 for you. So based on your tastes, based on what you are likely to watch, what is the top 10, like top 10 movies or something. And another term people use is contextual recommendation. Contextual refers to what is going on, not of the user, but what's going on in the world right now. So, for instance, during Black Friday, where electronics, people buy a lot of consumer electronics. At the time, if you go to Amazon.com, they will recommend consumer electronics because the context is of buying consumer electronics. These terms, I wanted to ground these terms because when you think of research problem, you think of application of cutting-edge research to industry, it is largely in this contextual personalized recommendation space. Okay, again, some examples. So B2C, for consumer, some examples of recommendations are homepage recommendations, what next, when you have watched a video, which is the next video that you sort of see on the right to watch. Social networks, people like in LinkedIn, they could recommend whom else to add as a friend. Note that this is a two-sided problem. If LinkedIn recommends me to add Nishant, then they also have to predict that Nishant will accept my invite. We'll go into the exact model of it later, but it becomes quite complex when it's a two-sided problem. Okay, and there are examples in the B2B space. For instance, there are companies which offer recommendation as a service, or for instance, in alerting, you can have what are the top events to look at. Like you might have hundreds or thousands of alerts or more, and we could rank them based on which ones you should look at. The ranking of tasks in a task management system, ranking of customer service requests. So some examples. Okay, the reason recommendations has been the single biggest source of growth for big tech companies like Google, Facebook, etc. By the way, online ads is an example of recommender systems. So why are recommendations important as to these companies? So recommendations are a growth lever. They're not a. They help a little bit in finding product market fit, but more than that, they come in when a company wants to grow. They want to increase usage. They want to find exactly they want to retain. They want to get users to find the first aha moment and then retain them. For instance, it leads to higher activation. When you open the Google Podcast app, first time, you want to know, what do I do here? At the time of the recommendation, if recommendations are good, you will quickly find a podcast. Okay, this sounds interesting. Let me listen to this. And once you have listened to it, then you know the platform. So this is called user activation. And once you get into a habit of using a platform, then that's called retention. So then you will come back. And finally, if I ask you after a month, hey, was this spending time on Google Podcast? Was that, I mentioned podcast because that's the product I built from scratch, but it equally applies to many others. But if I ask, hey, did this help? Did this time you spent, was that? Give me a 1 to 5 rating of, was that a productive time, use of your time? Did you like it? So that would be user satisfaction. I'll come to these terms later, because when you think about what are the objectives of my recommender system, you need to look at not just clicks. You need to look at user satisfaction as well. You need to look at retention as well. Okay. So we are here after many years of work by amazing researchers. I can only name a few because this, they're on a slide with John Riedel. He and others were participated in some of the early ways of doing personalized recommendation. So collaborative filtering methods, item recommendations, user. We'll come to that. But I spent a lot of work in personalized recommendations in late 90s, early 2000s. The three people in the middle, Yoda Corin, Stefan Rendell, and Jim McFadden, I had the good fortune of working with them in my time in Google. And to give you some idea of what they have done. So Yoda and Corin and Bell paper in the was used matrix factorization in the Netflix prize in 2007, I think. They brought a new approach to factorizing the user item matrix in a way that finds an embedding of a vector of each user, a vector for each item, which is sort of at the time was a big leap in quality. Then Stefan helped incorporating Stefan's work and helped incorporating context into this matrix factorization. So for instance, you might know features for each item. You might know what's its title, what's its description, its language, its length, its popularity. All these are features of the item. And Stefan's work helped making a model which incorporates that. Jim, you won't find much about him on the internet, but he and others, they they actually made it happen in this case in YouTube. So one, there's one, people do research, and then there are others who go to a company, typically a large company, because growth comes at a certain stage in a company, and then they build a proof of concept, show it, build it in a architecture, and it's such that it can scale, it is modular, and it works with existing systems, and then it slowly flourishes. And today, 67 billion hours of hi, is everything okay? Have I stopped sharing my slides?
The slides are still okay. Yeah, the slides also gone now. Yeah, can you? So something happened, disconnect or something. So can you reshare
Okay.
the slides again?
Yeah. Sorry about that.
It's sometimes this platform is a bit quirky.
Is it okay?
Yeah, now it's good.
Okay. So Jim was the architect of recommendations at YouTube, and then flourished. Jure Leskovich and Michael Bronstein and a few others have done seminal work in graph neural networks and applying that to recommender systems. There's a lot more to talk about this, and I've summoned the speaker notes, and I'll share the slides later. Okay, so let's ground it in actually how a system is architected. Recommendation system is architected. User visits a home page. They call in the home feed service, sort of calls the recommendation service as get a list of recommendations with the argument the user ID. That's the context of that call. Now, this service will look at, depends on how the model is implemented, but this service will look at the user. It'll try to find, let's say we are trying to, let's be very simplistic. Let's assume we have a map somewhere for this user ID, these are the recommendations. So it will look up the user ID in that map, get the recommendations, and serve it back. But broadly, this recommendation service, now having the user ID context, can look at all the user specific data, also can look at item data, item relationships, and make models pertaining to this user's history. That's how personalized recommendations are done. Whereas the modeling, this green user on the right, they're usually working on the modeling platform, which periodically infers and finds new embeddings or finds new like model parameters and inserts them into production. And these are the models, this green box cylinder in the left bottom. This is the one where the either the embeddings or the models are inserted and which are used in serving. Later, if you guys have, or even now, if you guys have questions on how serving of recommender systems happen, please feel free to ask.
Yeah. So let me just quickly try to summarize. Yeah. I see two main relations to be captured. One is the interaction between the user and the items or the products. Another is between items themselves, pairs of items, groups of items themselves. And the modeling essentially has to take care of both of those relations and embed it in some mathematical form so that when on the fly a request comes or user does some activity, the user can be shown useful results based on those features or embeddings that have been stored. Is that how accurate is that, and what is missing?
Yeah, let me. There are many parts. One part was missing. Let me start with that. So let's say you are doing a podcast recommendation service or video recommendation service, any content recommendation service. On the top right, you start with indexing. You scour the web or RSS feeds, and you find what is new content. You index it, find item metadata in a way that this same metadata should be available to you with the low latency map during serving. So for instance, you found the top 10 podcasts recommended for this user, then you also have to fulfill it. You also have to find the thumbnail for it. You also have to find the title description. So that's why this item metadata should be available also as a key value database to serving. This is used along with the user item interaction, like you said, the user item interaction and the item data. Both are used by the modeling platform, and that computes the embedding as needed. So the output of the modeling platform could be user embeddings and item embeddings. And now they're periodically inferred. These user and item embeddings are periodically recomputed and stored in this green database thing and the bottom left. And now recommendation service only touches that. So first it goes to, takes the user ID, finds the user ID, user embedding, and then searches with that user embedding what are the items that are close enough to it and returns that. Okay.
And keeps looking. So there's a search service which keeps looking for new items or
exactly. The indexing service at the top right keeps looking for new items, and as users interact with items, there's this arrow from the home feed service store interactions going down to the user item interaction data. So that's adding new, if I watched a podcast, that'll be a new event that'll be added there.
So this is a pretty comprehensive and complex diagram, right? A lot of data flows are happening here.
Yeah.
But broadly, you collect the new items, you embed them in a form, and then there's a deployment form where just the embedded. So it's sort of partition between these collection, embedding, and sort of lookup stages.
Yeah.
Okay. There are two questions right now. One is a little, okay, now the third one came. So the first one is about metrics. The second one is about what involves
periodic
inference. You can read the question. So please choose which one you want to answer or which one you want to postpone. Yeah.
Sure. So Asha, good question about metrics. So the question is, what are some of the ways to measure long-term impact from recommender systems, given A/B tests are not fully able to capture the long-term metrics, assuming most A/B tests are relatively short-term experiments? I'll come to that. There is a section on launch criteria, and I'll talk about metrics. If I somehow forget long-term metrics there, please remind me. Bhupendra asked what is involved in periodic inference. I think I mentioned it briefly. So for instance, if you have let's say you have a collaborative filtering model, which takes the user item interactions and finds the user embedding and item embedding. This is what I mean by inference, the actual computation of the embeddings. So you typically want to do it periodically. So let's say every 2 days, you are running this collaborative filtering process, which for all users and all your items finds new embeddings. Any comments on how to choose the proper candidate set to recommend? As number of items keep increasing, computation. I mean, I think that usually, I understand the meaning of the question. There are two stages. People look at design recommender system in two stages. I'll come to that. There's a slide on that. But yes, the first stage looks at all the items, shrinks it down to a small set, and then the second stage does a more thorough ranking of the smaller set of items. How frequently is periodic inference updated? This is a very product-based answer, and depends on the resources. There are also models which have a sort of streaming perspective to inference. We'll come to that. But the streaming part is actually, I would like you guys to think about. I'm sure you guys have done some of you may have done the system design question of Facebook or Twitter feed, where there are two ways. One is when a user logs in, you can fetch the tweets from their friends. Or the second is when a user tweets, you can figure out in whose lists that tweet should go and insert it there. One is optimized for computation. The other one is for faster serving to the user when they log in. That applies here too. So, for instance, if you can design an asynchronous recommendation system, which, in terms of inference, I mean, so which periodically, when a user item interaction happens, you can update the embeddings and store it, update it all the time. You should think about, I won't be able to get into it now, we can do it in Q&A later. You should think about when that is when you might do that, what sort of trade-offs would lead you to build that asynchronous service as opposed to night or every 2 nights inference for everyone. Okay. Yeah, so this is, again, ground ourselves in an actual implementation. One of the most successful recommendation systems algorithms is co-watch, or like recommend items to a user that are close to the items that they have already consumed. So I'll take an example from videos here. So let's say there are six users in your platform who, after having watched video 1, watch video 3. That's why the weight of the edge between video 1 and video 3 is 6. Similarly, every other weight, it's a directed edge. Every other weight refers to the number of users who have done that journey. After watching A, they have watched B in the next 8 hours or something, let's say. Now, that's your past data. The graph on the left is your past data. Now, let's say for a specific user, their history, like they call get recommendations. They say, okay, give me my homepage, and you look them up, look up their history, and you see that, okay, the video 1 and video 3, the ones in green, are the ones they have watched earlier. Okay, so now what we are doing is we are randomly, with the probability proportional to the weight of the edge, following an edge out of these seed nodes. Seed nodes being video 1 and video 3. We are sampling an edge out of these seed nodes. Let's assume here out of video 3 we sampled the one going to video 5, and let's assume from video 1 we sampled 3 edges going out to video 5, 4, and 2. So that gives you a sort of ranking of how which videos to recommend and which ones on top. This is how item recommendation is done. And co-watch is about, if you just used co-watch, you would get about 80-90% of the quality that you would get using the most sophisticated method today on a large recommender system like YouTube. It's very powerful. Okay, please feel free to ask questions if anything is not clear here.
And this process of following the edges can it be simulated by matrix factorization, or they are? Yeah.
Okay. The benefit of this is that it is actually simpler than that. It is transparent. There is no embedding to interpret. Yeah. Simply, we are keeping a map from every video to a list. So the key is the video, and the value is a list of other videos with scores, which also you can see and debug if needed. And for each user, the seed videos, they also have some weight. Like I might have watched 9 out of 10 times I might be watching Stanford lectures, and one time I might be watching NBA highlights. So that weight is also I can use in my how much importance to give to each seed. So while serving, all I have to do is look up the user's seeds, and then for each seed I just need to look up their lists.
Mm-hmm. Okay. So, and the drawback being that everything is explicit, so you have to store them efficiently and look up efficiently.
Right, right. So exactly. So the drawback here is one of rich get richer recommendations. So if I'm going to keep a list from each video, potentially this list can be of the size of my entire corpus.
Right.
And that's too much. So typically people shrink it down to, let's say, 200 items. And hence, what will end up happening is you'll stay within a large, popular video regime. Okay. Yeah.
There's a question from Upendra. Is it more like PageRank?
Yeah, I think personalized PageRank. If you look up the paper personalized PageRank, that exactly talks about this. Also, there's this paper by Davidson et al. In 2010, I think. That was the first YouTube paper that refers to this. Exactly. Okay. Again, just to ground it, this is what we talked about earlier. So when to serve get recommendations, you get a user ID. You find the history of that user ID. Here I've just used it as a list of item IDs, but typically you will have item ID and a score. Then for each element in the history, you find their co-watch lists, which returns a map from that the history item to the list of other items that people have consumed. Then you merge them because there'll be duplicates. Extract features, filter, rank, and fulfill. Some thoughts I'd like you guys to think about is, and there's a lot of work that goes on in big tech firms about these thoughts, is how to implement the data store that is needed for get history. On the one hand, you want it to be very cheap to insert to that data store. Second, you want it to be cheap to read from that data store. Also, you want to read soon after write semantics, because if I just watched a video and you'd want the next recommendation to that user to have that context. So so all of these are tough to implement. Another aspect is, we talked about this map from item ID to other list to the list of other items that people have watched, those edges. Yeah, you should think about what training infrastructure, like sort of MapReduce job, etc. What is needed to actually make that map. I think one of the things that I found most that I learned a lot after joining Google is actually seeing how that is done at scale. Okay. So previously what we talked about is item recommendation, and let me introduce user recommendation. I'll tell you why it's useful. So I could, when a user comes to watch movies, I could see, okay, this user is similar to all these other users, and they have watched this movie, so I'm going to recommend certain movie to them. Usually, this manifests is recommending top movies in a city, in a state, in a country, where the similarity of users is based on the geographical location. There are many models of user similarity, but in terms of privacy, this is also something I want you guys to know. As you might already know, privacy preserving recommendation is a very big research area, is a very big initiative in firms of all sizes. The problem here is that when let's say take a user A, I'm recommending user A has come to the app, we are trying to serve their homepage, we find users B and C are similar to user A. So now we have to access the history of users B and C while serving user A. This is sort of not privacy compliant. This sort of betrays user B and C's history to user A. I understand it might not be transparent which user B and which user C it is, but you can always come up with some pathological examples of how one can trace it back to a user. In general, you should avoid recommender systems which betray these aspects. So one of the approaches we used is to cluster users, and then we would find what is popular in that cluster, and then we would recommend items from that cluster. Now, in general, user recommendations are not as, in terms of quality, they are not as good as item recommendations. The advantage of user recommendations is that you can start from if you have history of a very small set of users, but now you have to serve many more. For instance, in building Google Podcasts, we had a history of just very few users, 100,000 users or so. And we had to now serve about 4 billion users that Google has. And this allowed us to do that, because we didn't have the item method would just not work for the majority of our users. Piyush asks how one handles cold start problem. So I think this is one way. This user is a cold start problem. The user we don't have history of the user, but we can find other users which are similar and they have history. Obviously, depending on the exact domain, there might be other approaches you can take. When I come to two-tower models, I'll tell you how the features of the item and the features of the user are used to handle the cold start problem. But you're right. So the cold start problem refers to, in general, that the traditional approaches like matrix factorization work when you have history of the user or history of the item. If you don't have nothing, it's a completely new item or a completely new user, then that approach does not yield any meaningful recommendation. Okay.
Yeah, and since you started talking, so cold start problem is probably the biggest. It is, I mean, almost a large number of discussions often get back to just how to handle the cold start problem, and there are. Is there a rule book of, if this is the case, this is cold start problem case 1, use this.
Yeah.
To use that.
Yeah, I think the general rule book is build your product intuition into the model. For instance, in terms of like when we come to the two-tower models, this model has a cold start problem. In this model, for each user and each item, we don't have any features. We are learning their embeddings from scratch. But what we learn is that, hey, but items actually have descriptions. They actually have, number of followers. They have other features. User has a location. They have, there's other aspects we know about both sides. So let's predicate the probability of watching, a probability of consumption based on those features, and incorporate that into our model and let the neural network kind of learn a good embedding.
It sort of sounds like, look where the information is or more information is, and build features around that first, right?
Yes. As long as you can capture the mutual information sort of those features and your recommendation, that's the best you can do. So technically, if an item is completely new, let's say you know that Lady Gaga videos are very popular on YouTube, and she posts a new video. Even if there's not a single user interaction with that video, just the fact that it's from this publisher should be enough to recommend it. Okay. So once you build a new, let's say you find a new approach, or you build a new infrastructure improvement, and now you want to launch it. this actually applies to more quality changes in non-infrastructure, but let's say you improve the algorithm and you want to launch it. What are the things you should see? And this will change from domain to domain, but in a content-based domain, we recommend looking at engagement, satisfaction, and responsibility. Engagements further subdivides into short-term engagement and long-term engagement, retention as they call it. So some metrics are, for engagement, you would see, I showed the user a homepage. What is the probability of the user clicking on an item on the homepage? Like, what is the observed probability? The click-through rate. Click-through rate could be item level or page level. In case of podcasts, one could also look at the average time listened per user per month, per day. So that's a long-term metric. The other metric people look at is L28, which means how many days out of a month or 28 days did the user come to the platform. So these are sort of engagement metrics. Satisfaction. So this sort of checks against clickbaity content. Like you can, or content that people don't feel good after consumption. You still want to ask the user that, hey, like how, what was your rating of listening to this podcast or watching this video or reading this news article? What was your rating? This has been very transformative. A lot of large companies have moved to rating-based launch decisions as opposed to purely engagement-based. Responsibility metrics are around, let's say hate speech or inappropriate content, etc. Unless you factor these into your launch decision, it's hard to control the health of your platform. I mentioned these not just as product decisions. Again, if you, let's say, find a new algorithm, actually, when you want to implement it, you will have to show its performance along all these criteria. And you'll find that there are approaches that look great mathematically, but once you start implementing it, you will find that they increase the bias of your system. They increase, sometimes it is possible that they are just suddenly recommending a lot of long tail content. And now that is increasing the offensive, like the fraction of content items that are marked offensive. So there are implications on these metrics for new algorithms. Recommending during searching. So Abhinav asks, recommending during searching, one may argue that users usually look at the first few items in a search result, okay? How can we ensure that the relevant search results always lie in the starting pool? Yeah, so I think these metrics kind of capture that. So our job is first to set the goals of the platform, the objectives of the platform, then write the metrics, then back it out as machine learning researchers, also practitioners, then back it out into a model which directly optimizes those metrics. So I'm going to answer your question as the click-through rate already factors that in. The page level click-through rate already factors that in. That if I have a wonderful recommendation for you at the 10th slot, I will get a lower page level click-through rate than if it's at the first slot. So once I have that as my metric, all I have to do is optimize for that in my ML model, and then have that as my launch criteria. Okay. Yeah. So we talked about. I think somebody was asking that do we recommend all items or do we index all items? Something like that. Yes. So stage one. In the stage one, so when you go to youtube.com, there are two stages. The first stage, it would look at your user embedding and look at all videos in YouTube and see which videos have embeddings closest to your user embedding. At this stage, every single video is eligible for recommendation, stage one. So this is in many billions. And that's why efficient vector database searches, efficient nearest neighbor searches has been necessary for this. If you want a resource on that, SCANN is, I believe, the best sort of implementation for this vector database search available today, open source. Then you have the stage 2. So after stage 1, you have, let's say, 100 or 200 items that are returned. And now in stage 2, technically, you might have multiple sources, so you'll merge them, like deduplicate them, feature extract, more ranking features, and then do a more, let's say, a more thorough neural network estimation of the probability of the user clicking on it. And then, then you will score rank based on them, and do diversity boosting, because you don't want to just recommend the same type of videos at the top. Diversity boosting, and then fulfill it with images and description, etc. Then serve it to the user. I'll stay on the slide for a second more if people have questions. This is also something that has been transformative. Like, this has enabled companies like Google and Facebook to achieve scale with their recommender systems.
I am curious. So there was a block diagram in the beginning, and there's this block diagram. And again, the retrieval.
Sorry, this one.
Yeah. So the retrieval, and then re-ranking, and then diversity. So that.
Where does that?
Yeah.
Where does that fit in, right?
Comparison possible.
Yeah. So the green recommendation service in the left is doing all of these 3 steps. I just did not write them as separate boxes, but this, let's say, the first step, the first step, it will be hard to move from this diagram, but imagine this rectangle recommendation service. It looks at, first takes the user ID, and it looks at this vector database and gets back the items. Then the rest of the neural network computation is, let's assume, inside this rectangle. So, so the top stage 1 retrieval, it needs a vector database search. Stage 2, yes, it needs some feature extraction, but is mostly running neural network and computation, typically done via RPC calls to a TensorFlow system, something.
And the filtering part and diversity boosting are also neural networks or machine learning based objectives, or the rules that determine those. Because specifying criteria for diversity is a very tricky thing.
Yeah, good question. I think diversity would be as a fascinating topic and a talk in itself, but I'll mention one thing.
Sorry, if I may, there's a question also. How do we bring in the diversity into the picture of recommendation?
Sure. Yeah. Sure. So let's say, let's take my example. Let's say I watch some machine learning videos, and I watch, let's say, NBA highlights, and let's say my daughter uses my YouTube account to watch Peppa Pig videos. Now, they have some, let's say these are the videos that YouTube finds for me. But it finds the probability wise, let's say, I don't know, let's say Peppa Pig has 40%, and let's say NBA 30%, and Stanford has 20%. Now, purely ranking by the probability of click, you would see a feed which is dominated by Peppa Pig at the top. And like somebody asked, I think, Abhinav asked that user will typically not go further down in their feed to find what is interesting. So right at the top, you need to bring in some diversity. A simple algorithm that was devised about 20 years ago is maximal marginal relevance. What it does, it chooses the first item, which is the highest click-through rate. Let's say in this case, Peppa Pig. Once it has done that, it adds a penalty to every other Peppa Pig video that, hey, I already have something, so reduce your score a little bit. So that means it will next pick the NBA video, I guess, and then add a penalty to other NBA videos and turn. The same method, exactly same method, is what we used in high frequency trading, 2006 onwards, and it's very, very powerful. Um, the it's grounded in very nice math as well.
So if I may quickly ask, so what is picking an action in high frequency trading? Is
So
it
when you have multiple strategies, you come in morning, come in every day to trade, and you have to pick. Typically, all of this is automated, but let's assume you're doing it manually. You have to pick among your 20,000 strategies which of the 10 ones to use in trading today. So you pick the one with the highest profits. The next one you do, but that one will have like maybe it does well on days in which there's a lot of trading, and on days when the volume is low, it doesn't do well. So that's a profile for it. Based on that profile, you can find other strategies which are similar and reduce the penalize the ones which are very similar to this one.
Yeah, so similarity between strategies is also something that needs to be measured.
Yeah, very good question. Is the degree of diversification personalized? So, again, think from a product perspective, that if somebody comes in, the first time a user has come into your platform, at the time you don't know much about them. You want to, you're kind of shooting in the dark, which means that you want to diversify more. They watched one single video. That doesn't mean that's all they'll watch. So again, you want to, next time they come, show a little bit of that, but also diversify. But now, let's say somebody, really well what their profile is. They just watch these 3 sets, and then, so then you want to diversify less. So it's about, your confidence of prediction. Okay. This general process that applies to to many industries, but in the case of recommendation, you have log data, process and transform. We validate whether there's which of the records have something wrong, which needs to be removed. So that's data validation. And you do model training. Then you check. Model validation is about, firstly, sort of passing some unit tests that, hey, is it actually sending the recommendations or not? Is it just sending empty recommendations for this set of sample users? Is it sending any non-empty recommendations? Second, you do quality, like on a held out set, you try to see what is the quality metrics, what are the quality metrics, and you see whether that's equal to, better, or not much worse than a certain delta from the previous version. And then you install it to the bottom half of the picture, which is production. Okay. And the aim of the slide is basically just to clearly state the difference between training and serving. Okay. So now we are starting to come to the part of the talk which is in the title, graph neural networks. I'm sorry it took us a while to get here, but
if I may wake up the audience, so how are you guys doing? Is the talk? Are you keeping up with the talk? There are a lot of us who are listening very intently. So do respond with a thumbs up or something like that. It's is it going well for everybody? Okay, a few thumbs up, great. Yeah. So feel free to ask your questions, and we have a great speaker today who has very, very diverse and information knowledge about this field. So feel free to get your doubts clear. And as I said, there are 2 questions coming in.
Yep. Sorry for jumping in. Are the individual components mentioned in 2-stage implementation still using the GNN type of models? A user need performance comparisons against variational neural networks. Right. So variational models, essentially a wonderful area, and I think underrepresented. Essentially add uncertainty into the embedding. Variation models say that a user embedding is not just a point estimate, but it also has a standard deviation on each dimension. It also has a variance. I think that is one way of approaching it. Another way people approach the same problem is by, and Pinner Sage is a very good paper on it by Joel Leskovich, which say that a user doesn't have one embedding, but it has 3, 5, 10 embeddings based on their history. But each of these is a point estimate. So variational models are successful, but they're not the only way to capture variation. The second question is, would be nice to see two-tower models motivated a bit. Yep, sounds good. So yeah, so that's why we're starting with collaborative filtering, where you have matrix of users and item interactions, and initialize user item embeddings with equal dimensional embeddings with random vectors, and then you using stochastic gradient descent. I'm not. This would equally work with matrix factorization, but I want to use stochastic gradient descent so that we can carry that thought forward in future slides. Using stochastic gradient descent, if a user watches a video, let's say items of videos here, watches a video, then by SGD, what we'll do is the embeddings of that user in that video will move a little bit, depending on the learning rate, will move a little bit closer. And we keep doing this on your entire set of user item interactions. At the end, you have user embeddings and item embeddings, which for any user which has watched a video, the dot product of their embeddings is going to be high. And if they have not watched a video, it's going to be low, which means that we have brought users close to the items that they have watched. This is matrix factorization, collaborative filtering. We have, it would be a stretch to call it two-tower models, but this is what Corin and Bell worked on in 2007. Any questions before I go ahead? So your input is a list of user, item, where a user has, let's say, consumed that item, watched this video. And your stochastic gradient descent starts with random embeddings and keeps updating them to reduce the loss. Okay.
So the trick and the challenge here is to get these embeddings right. Figure out the right models that get you the right embeddings.
So if there is no other information you have of the item, if there's no other information you have the user, this is the best you can do. If you just have a user ID and item ID, then this is the best that you can do. It has cold start problems. It has I think that is the biggest problem it has. It will give you exactly the same solution as matrix factorization.
Right. No, but even if you have a description of the item, and you can still smartly encoding it into features, or maybe you just come to yes.
Exactly.
Sorry, there's a question. Does this model inherently make it possible?
Because we are looking at both users and items simultaneously. Yes, exactly. So let's say I am a user. I have only watched again, NBA videos, etc. So what will end up happening is that my embedding, if trained this way, will be very close to the average of NBA videos that I've watched, and it will also be close to the average of Peppa Pig videos my daughter's watched on the account. It will also be closer to the ML videos that I've watched. So it will be literally the optimal solution here is the weighted average of all the videos that I watched in terms of L2 norm. So it does personalize. My embedding is very different. It completely depends on what I have watched. Okay, and in two-tower models, what people realize is, okay, along with the latent embedding, we are also going to add other information. So for instance, for the user, we can see what the user has searched on youtube.com. This is, let's say, YouTube recommendations. And we can also see what videos they have watched. I know that we were including videos watched here, but it's slightly different. You see here we are taking the entire data set and training the user embedding and using it the next day. There is no sequentiality of history. We are just hoping that the next day user has a very similar watching pattern. But here we are explicitly saying on March 1st, I'm going to use data user history till March, I guess February 28th, and I'm going to the user history. It is only till the point that you watched a certain video. And hence, I'm also mapping what is the relationship of the user's history till that time to this particular video that they have watched. This is a much more non-look ahead bias way of modeling it. Explicitly, if you want to see what this model is doing, it's making a very nice probability model, a probability of a user U watching a video V conditioned on everything we know, conditioned on user history, conditioned on what they have searched, conditioned on the terms in the video's description, features. And next step will be, in this model, we still have this latent embedding. We are still allowing it to learn something specific to each user. In the next model, we get rid of the latent embeddings. Now there is no cold start bias. There is not, when a user comes in, we are purely doing a math based on what we know about them and recommending based on that. So this is the difference.
So sorry, I missed the part about, so where is the latent embedding in the previous slide coming from?
So first we started with only latent embedding. First we said no features, just embeddings. We're going to learn from data set. Then we said we'll also add other things. And now the function we are learning is based on other things, and the part that is unexplained, we are putting in the latent embedding. Okay. And then now we'll say we'll handicap our model. There's no unexplained. You just have to limit yourself to what you know.
So for example, you could still do a matrix factorization and get that embedding and add it to the neural network generated embedding. Is that? So I'm just trying to see where.
Yeah. What is the difference, right? Here we could do that. This is actually, let's say, this can cheat. This can try to learn almost everything in the latent embedding. And then using regularization, you can force it not to, but so this can still have a cold start problem. Now there is no cold start problem. Now when Lady Gaga pushes a new video to YouTube, thank you, Gaurav. I'll come to your question. When Lady Gaga pushes a new video to YouTube, we just know that these are the terms in the description and publisher, etc. And we have to learn that Lady Gaga is a popular publisher. We cannot find an embedding of previous Lady Gaga videos that worked for them, but will not work for this new video.
Mm-hmm.
Okay, so Gaurav asked, where will item embeddings in user history come from? Are those learned? Item embeddings in user history, where they come from? Yes, very good question. So that's why I try to color code them similarly. You would ideally like to reuse the item embeddings on the top right rectangle, the one, and yeah, you'd want to use that in the left. So let's say you computed item embeddings today. Tomorrow, in tomorrow's data, on the left bottom, you should use today's item embeddings. And now you're starting to see how this is not a good way to visualize it. It's almost like a node is there in two places. That this item embeddings it's not a bipartite graph anymore. It's not two towers anymore. I won't go into this, but you can also use personalized search the same way, where you embed the query. But let's take this as the last slide, where your graph. A simple way to look at graph neural networks versus two-tier models is if your entity space has more than two types of entities, then it's a good, like for instance, you have users, you have videos, you have the terms that the user search, the terms in the description of the videos, you have publisher. In this case, it's much better to represent each of them with an embedding and to slowly morph their embeddings as events happen, as users watch a video, as as a channel publishes new videos. So what I want you guys to take from about graph neural networks is it is an improvement over two-tier models. It is as capable as two-tier models. By the way, two-tier models are virtually everywhere. Today, almost all personalized recommendations are by two-tier models. Very few have actually transformed to graph neural networks. I believe in the next 4 or 5 years, that'll happen. Most will shift to graph neural networks. They need to learn how to train those GNN models. That is where the industry is lacking. But they need to start visualizing it as entities in a graph, each of these having passing messages to each other when there is an interaction between them.
That's very good. So this is sort of the main transition from the past to present and future.
Yeah. Sorry, we're out of time, but graph neural network, this is how message passing works. The node in the red is updating itself based on its neighbors. I think you guys probably know, and please feel free to.
Okay, I mean, you could tell us more details about that also. I don't think the audience is
Okay. So I think one way people motivate this is by convolution neural networks. They say that if you look at in convolution neural networks, you apply a filter where center pixel in the next layer is equal to a weighted average of the pixels in the features in the previous layer. It's kind of weird trying to do the same. I look at it more directly. I think that whenever you have a graph, these graphs are the relationships that exist in real world. They are the ones. This node in the center, the red one, is being influenced by itself. Its history. That's why the blue arrow, and it's what is happening to its neighbors. So this is what the flow of information is. You can find parallels with it in chemistry. Chemistry is one of the fields which has worked best, drug discovery, etc., AlphaFold, etc. And social networks. And I think virtually all personalized recommendation at Pinterest is using graph neural networks. So here what will happen is you will initialize your graph with random embeddings and keep doing this update step. Exactly this formula at the bottom, you'll just keep doing it till convergence. I mean, usually convergence is a lot. You'd stop after some time, and that gives you your node embeddings. Well, the thing at the bottom, what it's doing is just saying that my HI, which is the red node, its new embedding is nothing but its previous embedding HI applied with weight transformation, plus a weighted sum of embeddings of its neighbors.
Sounds good. There's a question. When we have 3 entities, the graph looks like user, search term, item. The
user also has a direct edge to the item. Yeah, I think yes. I think you should have a user direct edge to the item, and the way to motivate is that here. Let's go here. Here also the user had a direct edge, as in the user embedding was made based on the terms salient to the user, which are embeddings of terms in documents in the user history or terms searched by the user. So if you have a conditionality in your model, then you should encode it as a node in your graph. typically, if you start with word models, etc., like BERT, etc., you will have very nice semantic embeddings of words to start with. So that is also one reason why you'd want to have um, these as nodes in your graph.
And I'm also curious about you have these two tower models, and storing embeddings is what are the sort of implementation problems that are new with graph neural networks compared to
Yeah,
previous models?
yeah. It's very hard to train. Like this is easy. Sorry, this is easiest to train. There is no sequentiality in it. You take the entire data set, you break it into batches, and you train it once. This gets slightly hard because you have to reuse the embeddings from here to there, and most people actually circumvent around that. It's a very hard. Why? Because you see, it becomes fundamentally serial and not parallel. You have to train the embedding, store it somewhere, use it in the next batch, and all of this over billions of data points and with GPU memory, etc. That's non-trivial.
Mm-hmm.
We usually don't initialize graph with random embeddings, right? As the learnable parameters are weights in the GNN, but not the embeddings themselves. So, okay, I think you are right that there are two things here: the W's and the H's. So the W's are the model, that's your graph neural network model, and you have to learn them, and the H's. So the H's are the node embeddings. While training, you are learning both. While inference, you are not learning the W, you are only learning the H's. But while inference, you will want to start H's with random embeddings because you don't know any better. And then you will want to run inference and arrive at the right embeddings. Okay, cool. Sorry, super out of time, but yeah, please feel free to follow up. I tried to cover a lot today.
And there's one more question.
Going a little off track, what do you think about federated learning of cohorts? Also, do you think that can potentially be the way to have a common recommendation for each user? Yeah, no, very big topics. Think about it this way. Here we have one application, users watching videos. Now, if you start putting other nodes in your graph, users reading news, users listening to podcasts, users other friends, you can build a graph. I think you have to prove that what you learn from one domain, crosses over to another domain, has application in another domain. And we have seen of that when we are building for podcasts, we did see that work, but it's not always the case. Okay, and federated learning, yeah, is a big concept, but again, this federated learning doesn't fundamentally change the model. As long as your user data is on device and you can communicate via updates, I think this is implementable via federated learning. Next question, let's say we have node features, doc2vec embedding only for the items in a user item bipedal graph. Would it be okay to pass the random features for the user and train the GNN? Yeah. So what you're saying is that I'm going to one way to put it is that your graph still has users and items, but each item node has a feature, which is your doc2vec embeddings. And so you first start with that feature, and then you learn your first layer item embeddings, and then you run your GNN inference. That makes a lot of sense. How to apply GNN to regression problems such as sales prediction? Yeah, I agree with you that a lot of times we talk in terms of the link prediction that we do, whether the user will watch a video is a classification task, but not always. Even in Even in like content platforms like YouTube, they try to predict not just whether, but how much they will predict. So that's just the output of your neural network. That's just the head of the model. I think you can use regression tasks. Also, does the GNN accept different dimensional features for each entity type? It does accept different dimensional features, but I think it does not accept different dimensional embeddings. At least I have not seen that. So I think in this, in this graph, for instance, the channel node embeddings, can it have a different dimension? I think that would be hard to implement. Good question. I certainly see why users need a bigger dimensionality, but I don't know if it's easy to do that.
I wonder if there is a way to partition the embeddings and keep everything together, but zeros for the ones, zeros for the other ones. That would be a very naive way to do it. But,
no, I understand what you're saying. Yeah. Implementation question. Could you apply the BERT idea of encoding time into the data set and to make it parallel? No. So so in a way, this is a long talk. It's about Michael Bronstein has this wonderful talk on comparison between transformer models and GNN models. But so in a way, positional encoding is trying to capture the relationship of the center with the neighborhood. And you can do that here, not directly. Every edge, there's no like edge that comes before or later than the other, but the nodes themselves have information that can be used to see how applicable they are. Like for instance, in case of positional encoding for this word, the one just before has a different relationship than the one two words before in a sentence. Similarly here, if two nodes of a certain type, based on their embeddings, the paper to look at is graph attention networks. That does capture this idea.
So temporal computation is also embedded in this. So as you go up the layers of graph, the temporal interaction is also captured. There are no copies of the graph, or there's another version of the model with copies of the graph also, or?
Yeah, I think the way I interpreted the question was more on positional embeddings. For that, I would refer to the paper Graph Attention Networks. But temporal aspects are best. There's a wonderful paper by Michael Bronstein on Twitter called Temporal Graph Neural Networks. If there's one model you want to use today for recommendation systems, I would recommend you to use that. I think that's the best in terms of implementation time, low latency, like the training time is least. It captures time. It's a nice blog in it. I won't have time today, but temporal graph neural networks.
I think the questions are still flowing, and I'm not sure, Gaurav.
No, I gotta go.
Okay, this is maybe the last question about
the question.
We
can stack up an MLP to the GNN where the MLP accepts the output embeddings, GNN input, and we can compare supervised. Yeah, perfect. Very good.
Yeah,
sounds good.
Okay, thanks a lot. Thanks a lot, Gaurav, for presenting us from the past to all the way to the future and patiently answering so many questions. And I'm sure our audience, it's almost 1.5 hours or more. I'm sure the audience has enjoyed the talk and learned a lot and got the chance to ask all the deep questions. It has been one of the most amazing sessions we have had. And thanks again, Gaurav, and the audience. There's a feedback form for the audience. I've just put in here. Please go. It's a short feedback, so please fill it, and it helps us understand you better and plan our future sessions better. So
thanks.
With that, thank you, Gaurav, and thank you everybody for joining. It's pretty late in India and from the other parts of the world. Thanks, and keep tuned to OffNote Labs and follow us on LinkedIn to for the future session. Thank you, everybody. Bye.
Thanks for having me. Bye.